So we're going to be doing a VTune workshop in here. Hopefully you've got VTune installed on your laptop. If you don't, now is a good time to do that. VTune is free. I have a few USB drives here that need to be shared. There's VTune installers on here, but they don't have license files. I think they work without a license file, but it's much easier to download a license file than the full machine. Than the full application. There's also a results folder on here. We're going to be looking at some pre-collected results together. So I would like everyone to copy the results folder off of here and then pass the USB to someone that doesn't have the files yet. So I'll just, you want to just pass those out? Well, there's installers that they don't need if they already have the tool. Right?
没有装的话，这边有那个 USB 里面有安装包的，有谁需要吗？那如果已经装了的话，那我们如果大家在跑的时候有任何问题的话，大家跟我说一下，我帮大家一起来看一下这些问题。什么？那个结果目录是？那个结果目录是我们 VTune 装完之后，它安装的那个目录上面就有那个 VTune 的结果的。然后另外的话，其实我们这一个安装应该都不用来，所以都没什么关系，你们直接装就可以了，装好了就 OK 了。
Okay, so should we wait like 5 minutes in the beginning to get people set up? Okay, so they need everyone needs the results off of here. Right? So we have Oh yeah, no. So we have some results to follow along with for everyone. So copy the results folder off of there, and then together we'll walk through them. Yeah. So just raise your hand if you have VTune installed already. Raise your hand if you don't have VTune installed. Okay, okay. Just checking if you follow the question. Yeah. So we'll wait a few minutes because it does take a few minutes to install VTune. And the USB sticks have copies of VTune for Linux, Windows, and Mac. So you should be able to grab the version that you need off the USB stick if the internet is slow. So James, so in the beginning I have an introduction to the tool where I can just explain the tool. Should I do that while everyone's installing, or should we wait for everyone to install? What do you think? Okay. Okay. So hopefully everyone understands the instructions. You don't have to install VTune. You can follow along with me, and that's just fine. But if you want to install VTune and follow along, the information is on those USB drives. Okay, so I'll go ahead and get started. Feel free to... Oh yeah, I don't even know if they need that address, but yeah, that's the license address. And my colleague James here in the gray can help anyone out. He knows a lot about VTune, so just raise your hand if you have any questions, and he can come around and help. So we're already in the first step, getting set up. Hopefully folks in the room are getting set up as well. I'll give a brief introduction to VTune. Hopefully you've seen a presentation here today or before, so you know a little bit about it. If you don't, then you will after I give my introduction. We'll look at a basic matrix multiplication sample that identifies a bottleneck in the code and how to fix that bottleneck. Then we will talk about Optane DC persistent memory, how you can profile that, and we'll walk through a sample for Optane DC persistent memory. And finally, we'll talk about Platform Profiler. For Platform Profiler, I didn't include any results. There are some pre-collected results with the installation of Platform Profiler that we'll look at, but generally those results are pretty large and they take a while to load into your server. So in the interest of time, I thought that wouldn't be worth it. So let's get started with a quick introduction to VTune. VTune is a powerful performance analysis tool that has a lot of different features, and it can profile a lot of different things. Whether you're interested in CPU performance, memory performance, profiling floating point operations, or parallelism, all of these things can be profiled with VTune. If you're using something like OpenMP or threading building blocks or MPI for scalability, we have metrics to help you optimize those as well. It's very easy to use. Everyone has probably used some type of performance analysis tool. Maybe it's Linux perf, maybe you've just used top on the command line to see the CPU utilization. Those are all great tools, but many of them don't have a powerful GUI like VTune. So you can see here, and you'll see in our demo, that there are a lot more things you can do with VTune than with a simple command line tool like Linux perf. It's very easy to get set up. You don't need to use the Intel compiler. You don't need to recompile your code or do anything special to use VTune. It will profile workloads that are just running that you've already built. You don't need to do any special setup. Also, since this is a workshop and it's a hands-on thing, if anyone has any questions, feel free to raise your hand and we can discuss them. We don't need to just go straight through the presentation. With VTune, setting up a profile is very easy. The first thing you do is you decide what do you want to profile. You can profile a single application by launching the application with VTune and profiling it as it runs. You can also attach to a running process. So if you have a long-running application that has a lot of startup and configuration, you don't have to start profiling from the beginning. You can have an application that's already running on your data center and tell VTune, go profile that PID, right? You pass the PID or the name of the process, and VTune can profile it automatically. You don't need to start it from scratch. Or you can profile an entire system. If you're interested in performance data for every application that's running at the same time on the system, you can profile system-wide as well. Once you decide what you want to profile, the next step is choosing the analysis type. Here you're seeing lots of different analysis types. A basic hotspots, general exploration, memory access. I'm going to turn off the microphone. If it's too quiet in the back, raise your hand and let me know if you can't hear me, okay? Can you still hear me okay, or is it too quiet? You can hear me? Okay, good. So there's a lot of different analysis types you can do, and the one that you choose determines what type of data is collected. So if you choose hotspots, you're just going to collect data about where you're spending time. What are the hot functions? What are the hot processes? What are the hot lines of source code? If you want to get more detailed analysis, you might choose something like a memory access analysis. This one's going to profile the caches and the DRAM on your system, so you can see if you have bottlenecks in the memory subsystem. And there's some more advanced ones as well. I'll talk about this one here. It's called General Exploration or Microarchitecture Exploration, and we have ones for parallelism as well. If you want to learn about your threading, whether you have performance issues due to synchronization like mutexes and locks, VTune can give you a lot of information for that as well. Once you choose what you want or what type of analysis you want to do, you can change the knobs if you want to. There's default values for all of this data, but as you become more of an expert user, you can configure everything. You can choose the exact type of data that you want to collect, the sampling frequency, and 100 other things as well. Then you push start, and the profile starts. Right? So you can see with just a few clicks, the data starts getting collected. There's a very powerful GUI, but there's also a full command line available. So everything that you can do in the GUI, you can also do from a command line. If you have a Linux cluster and the profile needs to run there, you don't have to install this GUI on your cluster. You can actually configure everything in the GUI on your laptop, and if you push this button here, a box pops up and it says, here's the exact command that you can run on a machine to do this analysis. So you just copy that command into the shell, and you can run an analysis without needing the GUI. Any questions so far? So for the people that just joined us, we're going to be walking through some examples together. There should be some USB sticks floating around with the VTune installation files on them if you don't have VTune already. And there's also a results folder with some pre-collected data that we can look at together. You don't have to follow along on your own laptop, but if you want to, because this is a hands-on session, that's available. Is there anybody that still needs those files? Raise your hand if you need the files. Okay.
将那个 USB 互相传一下哈，如果考完的话跟我说一下。谢谢。还有些没有考里边的那个结果吗？
Okay, and again, I'll be showing everything up here, so if you just want to follow along with me, that's okay also. Yeah, and all of the information from the summit will be made available to you. So even if you get behind and you can't quite follow along, you can look at all of this stuff offline, and you'll be able to, take your time and go slowly through. One concept that's important to understand about VTune is the way that it collects data. VTune has two different collectors included with it. It has a very basic software collector that uses OS interrupts to profile the applications. So every 10 milliseconds, for example, it will interrupt the application and collect data like the instruction pointer, the call stack, kind of basic information for understanding your hotspots. This one can work in virtual environments. It can work basically anywhere because it only operates in user space and requires no special kernel driver. The more interesting type of collection that VTune can do is using this hardware collector. The hardware collector reads the PMU registers on the Intel chips. So every Intel chip has registers that are called performance monitoring units, PMUs. And these registers collect events like L2 cache misses, or branch mispredicts, or instruction fetches. And by collecting all of these events on the processor, you can understand where you have good performance and where you have bad performance. This collector does require a driver that you'll need to install, but if you're on Linux, it can use the perf driver. If people are familiar with Linux perf, VTune can use the Linux perf driver. On Windows, it has its own driver that needs to be installed. Any questions so far? Yes. And sorry, just really quick, if you feel more comfortable asking a question in Chinese, James can help translate, so you can choose.
If I run my application in a container, is it okay for both ways?
Yes, in a container, both ways work. The hardware collector has some limitations with containers depending on the container. So similar to virtual machines, the container has to make the performance monitoring events visible from inside the container, but as long as that option is enabled, then VTune can run inside a container, outside a container. It can run both ways.
You mentioned the Unix code.
Yes.
So this is only for Intel driver.
Yeah, so the only thing you need root for is installing the driver. Once the driver is installed, users can use the driver without needing root privileges.
Okay, so I need to install this.
Install as root, yes. And then or if you can't do that, if that's a limitation for you, if your kernel provides access to Linux perf, which is the default performance monitoring driver in Linux, you can use that instead, and you won't need any administration. Any other questions? Okay. I keep pushing this button, but I never plugged it into this. It's fine. So what do you see with VTune? And we'll see this in a live view as well. Here we're looking at a summary view of a hotspots collection that was run. And some of the information you'll see are things like the elapsed time. How long did I run the collection? In this case, 5.5 seconds. CPU time represents the sum of all of the time on all of the CPUs. So if I had 4 CPUs and my application ran for 5 seconds, it could be as large as 20 seconds of CPU time, right? If you use the hardware collector, you might see things like instructions retired. This counted how many instructions were retired. CPI is cycles per instruction. And here we're seeing hotspots, memory bandwidth, and a CPU usage histogram, giving you an idea of how well the cores were used. when you drill deeper, there's other viewpoints available. So I was on this summary tab here. Now I'm on the bottom up tab. And in the bottom up tab, we have three main pieces. We have a grid that is organized by the grouping. So in this case, it's listing functions, but I can customize that as well. We have a timeline, which I think is probably the coolest thing about VTune. It's hard to get this kind of visualization from a text-based tool like Linux Perf or Top or some command line thing, right? But with a powerful GUI, you can actually see all of the threads, when they were running, when they were created, when they ended, and whether you have good parallelism, right? So in this case, we had some OpenMP, but for most of the application, there was only one thread running. Then at this point, I got some more threads running and some good parallelism, but a lot of the application was serial, right? If you have multiple cores available, hopefully you're using some sort of parallelism. The red here is also showing where you have overhead or spin time. So if you use something like OpenMP and you have spin wait locks, where the thread is actually just spinning, saying, is the lock ready, is the lock ready, is the lock ready, it can look like you have high CPU utilization, but it's actually not making forward progress. It's not doing good work. It's just spinning, waiting for the lock to become available. So you might see 100% CPU utilization and think your application is great, but really it could be a lot of spin and overhead time in your threading. Any questions? Okay. The type of analysis that VTune is most well known for, and hopefully the type of analysis that you all are interested in, is the microarchitecture analysis. This is the analysis that's going to show you how efficiently are you using the CPU pipeline, right? So every core, when it puts instructions through the core, it uses a pipeline. The instructions go through various stages, from instruction fetch to execution to retirement, and anywhere along that pipeline, you can have a bottleneck. If there's stalls in the pipeline, everyone has to wait for those instructions to complete. And that's really hard to visualize without a tool like VTune. So VTune has this microarchitecture analysis to help you understand what part of the pipeline is the bottleneck. This is an example of how you could run this as a command line, but you could also run this from the GUI as well. What you're going to see after you run a microarchitecture analysis is a bunch of metrics in the grid. And these metrics all represent some sort of performance issue in your application. If you have high values, usually that means you have a big performance issue. We could spend a whole day talking about all of the metrics that are available, but we don't have time for that, so I'll just talk about a few of the important ones. The four listed here are front-end bound, bad speculation, back-end bound, and retiring. Front-end bound tells you what percentage of the time is wasted by the front end of your pipeline. The front end is responsible for fetching the instructions from the binary, decoding those instructions into machine code, and passing them to the back end. So if you have a binary that has a lot of jumps, a lot of far branches, right, then it's very difficult for the front end to fetch all of those instructions in order, and you might get front-end bound issues. Or if you're using interpreted code, like Python or Java, those codes are not laid out nicely in a native binary, right? Those codes move through an interpreter, and they often have front-end issues. The back-end bound category is how much time you're wasting in the back end. The back end is responsible for fetching your data from memory, executing the instructions in the adders or the subtractors or the dividers, and then retiring those instructions. This is the most common place that we see performance issues, and the most common reason is the memory subsystem, right? An add might take one cycle. Going to DRAM takes hundreds of cycles. So really quickly, you start to see where these bottlenecks come from. They come from the memory subsystem. The bad speculation category is the amount of time you're wasting doing work that never retires. So if you have branch predictors that are mispredicting a lot, you'll be executing instructions on the wrong branch, and that work has to get flushed out. And the best category is retiring. These are the instructions that move through the pipeline efficiently without getting stalled. Right? So not only do you get these metrics in a summary view, you actually get them at every level of the grid. So now, to understand this grid, I could tell you that my initialize 2D buffer function was very efficient. It was retiring 100% of the time. Whereas my grid intersect function wasted 46.4% of its cycles in the back end. And that's useful, but it's not the best data that you can get, right? You still don't know, well, where in the back end, right? Was it the memory system? Was it the core? Was it DRAM? And luckily, VTune helps you dive into those details. Just one more thing I'll mention on this slide is you'll see some of these cells are highlighted pink, or it doesn't come through that well here, but every metric has a predefined value threshold. So we put a value in there and say, if you're outside that threshold, we'll highlight it for you. These are the locations we think you should go investigate. These are the places that we think are the biggest performance issues. Any questions so far? Okay, and we'll look at an example. The matrix multiply that we're going to look at together is a microarchitecture analysis where we find a bottleneck. The great thing about VTune is it doesn't just provide these high-level metrics, right? For each of these metrics, they're expandable to sub-metrics that are related to the parent metric. So for example, if we were looking at this result and we were interested in figuring out what was going on with the grid intersect function, well, we know it's in the back end. 46.4% of my pipeline slots are stalled. So I can expand this metric by clicking on it, and if you have VTune installed and you open up the matrix result, you can do this. And now I'm seeing it broken down by memory and core. What percentage of the time am I stalled in the memory system? What percentage of the time am I stalled in the core? And I can break it down even further. What percentage of the time am I stalled by the L1, the L2, the L3, DRAM? What percentage is related to stores? Right? So now you can see with this hierarchy of metrics, it's very easy to drill down to the exact performance issue. Right? It's not just, oh, your application has a memory issue. It's your application in the grid intersect function has an L1 cache issue. Right? So now, if it even just got you that far, that would be great. Right? You could go look at the grid intersect function and figure out why it has problems in the L1 cache. And here, it actually goes deeper. It could be DTLB, it could be 4K aliasing, it could be the fill buffers. And VTune has very detailed documentation. So for every one of these metrics, there's a long description of what that metric means, what could cause that problem, and what can a developer do to try and fix that problem, right? VTune doesn't change your code for you. Unfortunately, we can't fix your problem automatically. The developer still has to go in and change the lines of source code, but we try and get you as much information as we can so that you have the easiest job tuning your performance. In addition to reading the documentation, it's built into the GUI. So for all of these metrics, if you hover over one of them, you'll see the description. And you'll see links to help documentation as well. Okay, so that was a brief introduction to VTune. Now I'm actually going to open it up and look at the matrix sample that's included in those result files, and we can walk through them together. Any questions so far? Okay. I hope some folks have VTune installed and have the results open. If you don't, raise your hand and we can get you the results files. It'll take a little while to install VTune, but copying over the results should be very simple. So let me switch over to my VTune, and if anyone needs help or has questions, raise your hand and James can come around. So this is VTune Amplifier. When you open it up, it runs on Windows, Linux, Mac. So regardless of what laptop you have here today, hopefully you can open VTune on it. And what you'll see first is just a welcome page. Here you can set up a new project, configure the analysis, open up some previous results, go to the documentation, whether it's online or the included documentation, some links to articles, that sort of thing. For us, the first thing we're going to do is we're going to open up that matrix sample. So I had the link on the previous slide, but basically, now I'm in VTune, running the slides. You should have copied over a results directory that has a matrix directory in it. Inside that directory, we collected these results with Visual Studio, so there's a VC14 directory, then a VTune Amplifier results directory. Under that, there's a matrix directory, and there's this project file. So hopefully you can open up that file in VTune, whether you double-click it and it opens the GUI. If that doesn't work, just go to VTune, navigate to that location, and open it up. So I've opened it up like this. I guess I can just walk through it too. So if I went to this, and then I went to Open, Project, I navigate to this matrix directory, and here's the project file right here. So if I opened up that project, then I would have the project opened up in my GUI. And you can tell the project, yeah. Go ahead. Okay, if you don't see the project directory, just open up the result. Just go to that one. Just either one. Go to 0 first. And open up that file. Yeah. So that's just the result instead of the project. Yeah. So if you aren't able to open up the project directory, you can open up the results individually. And if you go into one of the results, let's see, for example, if I go into matrix, the individual results will be in the results directory, and you can open up those individually. So these files here can also be opened in the GUI. So if you just open up result 0, you'll see a representation of the microarchitecture exploration that I was explaining. First, what will open up is the summary view. So here I've got a matrix multiply, and it's pretty clear from the red color that I have a big performance issue. So this matrix multiply took 31 seconds, but it was 90% bound by the memory subsystem, right? And I can see a bunch of different metrics here in the summary. The CPI is very high. CPI should be somewhere around 1 or lower. If you want to have a very efficient program, you want your CPI to be very low. And as I drill deeper, it becomes clear. I guess I can just do it here because it's a real thing. So if I was to just have this closed like this, I can see, okay, it's a back-end issue. Let me dive deeper. Oh, it looks like it's a DRAM issue, right? So I'm DRAM bound. Let me go to the bottom-up view here and see what it tells me. The bottom-up view has a grouping right now of processes, then functions, then threads. let's take a minute to investigate that grouping and how it can be configured. So right now, I only profiled one process. I profiled matrix.exe, and if I want to look at the functions in matrix, I'll just expand that, and it will give me a list of all of the functions that were in matrix. Here I can see it's really just one main function taking all of the time, this multiply to function, which is my core compute. And I can see if I wanted to, how many threads, if I drill deeper, I can see my 4 worker threads, and how much time was spent in each of those. I have a good load balance. Each worker thread is doing 24 seconds worth of work, and you can see in the timeline there's a good load balance. Everything runs for the whole time in parallel, but there's still a big performance issue. I still have a big DRAM bottleneck. It's good to know the function, but some applications have huge functions. Right? A function could be 10,000 lines of code. So function names are good, but they're not quite as good as it can be. It would be better if we could actually drill down to the source code. And VTune can do that. So if I double click on one of these functions, this is what you guys are probably going to see. Because I shared the result with you, you don't have the same paths set up for the source files. Locations of the source files on your system are going to be different than the system where they were collecting. So all you need to do is point VTune to the location of the source file. So I double-clicked on that function, and VTune is saying, where is this multiply.c file? So I'm going to tell VTune where my multiply.c file is, and you should tell VTune where your multiply.c file is. It's going to be in the source directory of that multiply result, right? So I'm going to go here, I'm going to browse, I'm going to go up to the matrix directory where I had that VC14 directory, and I've got a source directory here. I'll go into the source directory, I'll point it at the multiply.c file, and I'll click OK. So this is the kind of thing you'll need to do if you run a collection on a cluster somewhere, and then you want to analyze the data on your Mac laptop. The only thing you'll need to do is point your Mac laptop to those source files. Right? If they're on a file share somewhere, you just say, here's the paths to the files, and VTune will automatically go resolve this information. So check this out. I double-clicked on the function, and now I actually see those metrics broken down by the C++ source code level. Right? So not only do I know that it's a certain function, I know that it's line 198 that's doing this compute right here that has all of these performance issues. Right? Now, this is the point where I might say, does anyone know why this is a bad matrix multiply? Think about it, but I won't put you on the spot. I won't pause here and ask everyone why it's a bad matrix multiply. But if you look at it in your own GUI, or if you look at it up here, think about it for a minute, why this would have memory issues. And the issue here is the way that you're walking through memory in this matrix multiply, right? This is correct code. This will give you the correct answer. All of your regression tests will pass. You can ship this code and nothing will crash. But there is a huge performance issue here. Right? And that's why we're all here. We want to debug our performance issues, not our correctness issues. And the performance issue here is related to this two-dimensional array, or this matrix, B. If you see the inner loop uses K as the iterator. And K is the first reference for the matrix B. So what that means is every iteration of this loop, B is going to have to jump a whole column in memory. And this matrix, the way that it's laid out in memory, is every element in the row is next to each other, and then the next column comes after that. So if you want to walk through it in memory, you need to go through the rows first, and then the next column. Go through each column in a row, then go to the next row. And go through each column in that row, and then go to the next row. That's how you'll get spatial locality walking through this matrix. This developer didn't really care, right? They just wanted to write a correct matrix multiply. But every time they go through this inner loop, they're losing all of their caches, right? They have to jump, depending on how big the matrix is, maybe they're jumping, 2048 integers away, right? Which is not good for your L1, L2, L3 caches. It's causing the user to have a lot of cache misses. So really quickly, we found the exact issue in this code. This line of source code has a bad memory access pattern on this B array, and it's amazing how easy this problem is to fix. If you open up result 1 the same way that you opened up result 0, we can see a very simple fix for this performance issue. And now, if you remember, result 0 took something like 30 seconds. Result 1 took 2 seconds. All right? And the whole reason was because of a really big memory issue. Now if we look, we've taken our DRAM bound from something like 90% down to 27%. And the memory issues are more in the the DRAM bound, down to 27, and now the memory issues are more in the L3 and the L2, which are much faster than DRAM. So we can see the application got a lot more efficient. The CPI went way down. Now it's 0.7. It used to be something like 16. And let's look at the source code and see how many changes we had to make that happen. So first I'll go to the bottom-up view. The bottom-up view is going to show me my hottest functions, and I'm suspecting the hottest function is still going to be multiply. Right? Let's see. Oh, it's grouped by process, so I'll expand. I'll look at the functions inside my process. And now I've got this function called multiply3, where all of my time is being spent. And if I double-click on that, it wants to know where the source file is, so I will point it to my multiply file. And it will take me to the exact line of source code where my multiply function is taking up all of the time. Right here. The only thing I did, well, I added some vectorization as well, but the main performance issue was just changing. It used to say IJK, now it says IKJ, and every matrix is walking through the columns before they walk through the rows. Right? Really simple fix. Obviously, this is a basic example, but it made a huge performance improvement, right? So the key takeaway here is just because the code is correct doesn't mean it's going to perform well, right? Things like memory access patterns, parallelism, vectorization, those things can have a huge impact on performance, and in order to diagnose those issues, the best thing you can do is use a tool like VTune, right? So I just want to show you a few more things in VTune in the matrix multiply example, and then we'll start looking at an Optane DC persistent memory example. Any questions about what I've shown so far? Okay. So I'm just going to go back to the bottom-up view here and show you some cool things you can do in the VTune GUI. So right now I have a grouping of process and then function and then thread, but that's fully customizable. So by clicking on this hammer icon here, I can change the grouping. And one of the things that I really like to do is I like to see whether my software threads are jumping around between cores, right? It's really good for performance if you can keep your threads on the same cores, because that means the data they're using is in the cache of that core. But if that thread, if the OS moves that thread over to another core, that core doesn't have the same data in its L1 and L2 cache, right? So you may have heard of something like thread affinity or pinning threads. And so let me create a grouping that will show me that really quickly. What I'll do is I'll change the levels of this grouping.
And the first thing I'll do is I'll put threads. So I've already got threads here, so let me just move it up. And then I'll go and I'll find cores, which are hardware cores, and I'll put those here right underneath my threads. Save that grouping, and now you're seeing right up here, the grouping has changed, and now I'm seeing all of my software threads. I had 4 OpenMP threads, and then some other threads that weren't really doing anything. Let me look at this first one. Because this was well parallelized, I'm guessing that it probably didn't have to move around too much. And actually, now that I mention it, this was run on my laptop, so I don't have a ton of cores. But I can actually see, surprisingly, this thread did not stay on the same core. Right? This thread spent about equal time on all 4 cores on this machine. And if you have a 4-socket machine, 156 logical cores, really quickly moving those threads around can cause a big performance issue. Right? So if you want to figure out whether your affinity is working correctly, there's a question here. Or if you want to figure out whether your threads are jumping around between cores, VTune can do that for you. So I'm seeing my software threads and what cores were they running on. Right? And the way that I did that was just by changing this grouping here. I can also see things about hyperthreading. Actually, this machine is not hyperthreaded, but in addition to cores, you can break this down by hardware contexts. So you'll see the logical cores if you have hyperthreading enabled. And there's probably 25 different things you can add to the grouping here. If you want to see data by module, right, you have one big process and a lot of different shared libraries that are linked in. Different .SOs or different DLLs on Windows. You can see the time broken down by that. And then you can determine what engineer is responsible for that code and tell them, hey, look, I see that all of the time is spent in your shared library. That's a performance issue. Please go fix that. Or if it's a third-party library, you can say, yeah, well, there's nothing I can do about it, right? But understanding where you're spending your time is very important. There's also metrics related to OpenMP. There's metrics related to modules, processes, basic blocks, code locations. I won't talk about all of these. They're all documented. But you can see that it's not just about hotspots. You can diagnose hardware issues, affinity issues, OS scheduling issues. All of that data is available once you become a power user of VTune and you understand all of the ways that this data can be sorted, then you can do some really neat things. One other thing I'll mention about the VTune GUI here is the ability to filter. So you may collect data about 10 different processes and 100 different threads, but really you're only interested in one. Or you're only interested in a subset, or you're only interested in a time slice. Well, VTune has the ability to filter as well. So let's say, for example, I saw something interesting on this timeline. There isn't a lot of interesting things in this example, but I can still show you how the feature works. Let's say I saw a spike in CPU utilization, or I saw a dip in CPU utilization, and I wanted to know what's going on right then. What exactly is happening on my machine that's causing that? Well, I can actually select that region in the timeline by clicking and dragging, and then I can do a zoom in and a filter in by selection. What's going to happen is it's actually going to update this grid with just the functions, or in this case the threads, right, that were executing at that time period. So we'll see, what did I zoom in? About a few hundred milliseconds, maybe a couple hundred milliseconds, and this grid updated to show me exactly what was going on that time period. So if I change this grouping back to function, it's going to look similar to what we saw because there's not a lot of interesting functions in this application. But we've seen things on customer codes where there's a dip in CPU time, and you zoom in and you find out that it went into the kernel, right? Something serialized, maybe a logging function in the kernel happened, or some function that doesn't get called very often happened, and that function is serial. It's hard to know until you have a tool that allows you to zoom in like this. So by being able to zoom and filter with the data that you've collected, you can drill down to the exact location of your problem, filter out everything you're not interested in, and determine what was going on when this interesting thing happened. Right?
So you can do that in VTune by zooming, filtering, and the grid and the timeline are tied together. So whatever you zoom in on here, it's going to update here. Right? So maybe a lot of the time you have the exact same thing happening, but one small piece of time something interesting happens, you can zoom in on that and figure out exactly what was going on. Any questions about what I've shown? Okay, yeah, question.
Yeah. What is the sampling interval of this example?
Good question. So for this example, so the question is, what's the sampling interval?
Yeah.
And maybe at this point I should kind of step aside and explain exactly how this collection happens. So all of these collections that we're doing are statistical sampling, right? When you're doing performance analysis, you cannot be a high overhead collector, right? If your collector has 100% overhead, then the data that you're collecting is not representative of the data that you're looking at, right? You have to be low overhead. And in order to be low overhead, you have to do statistical sampling, right? You can't actually look at every instruction. You have to take a sample every so often, and once you have enough samples, you have a statistical representation. You can see here that the sample, oh, maybe you can't see, it's not great, but if you go to the Analysis Configuration tab on your own result, the sampling interval is 1 millisecond. And this is configurable as well. So one thing to note here is that's kind of the time ranges we're talking about with VTune. If you have a workload that runs for 2 milliseconds, VTune isn't really designed to profile that with these types of analyses, right? A 1 millisecond sampling interval is no good for a 2 millisecond application. Or if you have a workload that's running for 15 hours, these type of analyses that I was showing you aren't really designed for that. We have another tool called Platform Profiler that's better for those longer running applications. What we're really looking at with these analyses are a few seconds, several minutes, a time slice, right? A lot of applications are doing the same thing over and over, and once you look at a time slice, you get a good idea of what's going on, right? But that's not to say there's only one size application or one size you can profile. Because this is all configurable, you can increase the sampling interval if you want to run for longer. You can decrease the sampling interval if you want to profile a shorter running application. But we're not looking at a few milliseconds or tens of hours, right? Somewhere in the middle. Questions about that? Okay. So next, so this was just a code that was running on a CPU with some DRAM. There's nothing here about Optane DC. I know a lot of people here are trying to learn more about Optane DC persistent memory. This is PMDK, SPDK Summit. So VTune has built-in capabilities for Optane DC persistent memory as well. So next what we're going to do is we're going to walk through kind of a very simple example that explores the performance of Optane DC, the performance issues with Optane DC, and the way you can see those with VTune. So there should have been another directory in that results directory with a PMDK example. I'll open it up here, and you can follow along if you have VTune installed. So I have a PMEM bandwidth case. I have a project file here, and I'll open that up. It'll close my previous project file. And then let me jump over to the slides actually before I do that, because I have some slides that walk through it. So we did the matrix sample, right, that you all have access to now. Now we'll do a persistent memory bandwidth case. So what we did here was we set a goal. We kind of knew the performance characteristics that are published of Optane DC persistent memory, and we wanted to see what kind of kernels we could write with PMDK and how they would compare to the published goals. So we started out with a very basic PMDK application here. And what we're doing here is a very simple kernel, similar to something, if you've ever seen a stream benchmark to measure DRAM bandwidth. We've got a kernel here, except now it's using Optane DC persistent memory. These macros here are macros for reading and writing to persistent memory. We have a parallel for loop, and we're doing kind of a very simple multiply and add in a parallel for loop. When we run this code and we profile it with VTune amplifier, we get this data here. I've got it in the slides, but I'll also open it up in VTune. So let's open it up in VTune, and we'll see it peaks out at about 12 gigabytes per second, much lower than we're expecting. And let's open it up. So this one was the original. I will go here. I will open up multiply and add original. And I'll see another summary view, right? So in this case, I did a memory access analysis. The last one was a microarchitecture analysis. And you'll notice that the summary view looks very similar, but the data is a bit different, right? So now, in addition to seeing things about the L1, L2, and L3 in DRAM, I've got a metrics here. I've got a metric here about persistent memory. I'm seeing there's quite a bit of time wasted accessing persistent memory. I also now, in the memory access view, have a bandwidth utilization histogram. So I'm seeing that for DRAM bandwidth, most of my time is spent with a very small amount of DRAM bandwidth being used. I can change this to a persistent memory bandwidth histogram. And now what I'm seeing is how much persistent memory bandwidth am I using, broken down by the amount of time spent at each of these levels, right? So this is the x-axis here is gigabytes per second, and the y-axis is seconds. So this bar means, maybe 11 gigabytes per second for about 4 seconds. And we saw in the summary above that the average, or we saw in the slide, excuse me, that the average was about 11 or 12. So that's actually probably 12. So that's what that histogram is showing. Now if I go to the bottom-up view, this one's going to give a timeline at the top because the memory access analysis is really about showing you memory bandwidth, and now the grid's at the bottom, but it's basically the same as what we saw before. Now the grid is showing functions. Parallel for in my main is my biggest function, obviously. It's a very simple kernel. And my persistent memory bandwidth is about 12 gigabytes per second. And you can see that a significant part of it is due to persistent memory writes versus reads. Reads are still the biggest part, but there's a significant amount of writes. And if you've attended any of the presentations on Optane DC this week, you should know that write bandwidth is much lower for persistent memory. The writes have much higher latency than the reads, and the more writes you do, the more your performance is going to be impacted. So instead of doing a lot of writes to persistent memory, let's see if we can avoid the writes. So how can we do that? Well, before I was writing to this array in persistent memory, right? In this case, I've removed that macro to write to persistent memory, and I'm just writing to DRAM. I'm still reading from persistent memory with these macros, but this is allocated using a standard malloc instead of a PMDK allocate. And really quickly, you can see that has a huge impact on performance, right? So if you were doubtful that writes have that are not impactful for persistent memory, here's some data to refute that, right? Now you can see the writes in blue, much thinner than they were before, and the bandwidth has almost doubled, right? So here's the name of the result that you have access to. I'll go ahead and open it so we can look at it together. But let's just call out that there's a significant bandwidth improvement, and we can look at the code in VTune. So now I had my original result open. I'm going to go ahead and open the second result. Any questions? So I've got this read-only result where I've changed the PMDK write to a normal allocate in DRAM. And if I go to the bottom up, I'll see the screenshot that was captured in the slides. Again, you can do things like zooming and filtering. You can see multiple packages. So I haven't mentioned this yet, but if you're on a multi-socket machine, you'll see the bandwidth from each socket.
In this case, I only have persistent memory attached to socket 0, but let's look at DRAM, even though it's not particularly interesting, just to show you what you can do with VTune. Here, I've expanded the DRAM, and I'm actually seeing broken down by channel, right? So, if you attended my talk where we talked about configuration of systems, here you're seeing some of that channel data, or that configuration data. If you have all your channels populated, and you have all of them streaming data equally, then you're getting a lot of available bandwidth. But if you only see data streaming from some subset of channels, you may have a configuration issue. You can see in the grid, just like we saw before, metrics related to the caches, the DRAM, and now an additional metric related to persistent memory. So if you run an analysis on a machine that has persistent memory, VTune will automatically show you persistent memory metrics. It can detect the persistent memory and show you those metrics. You don't have to do any special configurations.
So it's package is a socket, right?
Package is a socket, yes.
Right.
Yeah. And so that's another way that you can sort the data. I didn't show that, but if you wanted to change the grouping here, you can go by package and then hardware context, right? So if you want to go by package or socket, you can see how much time is spent on each socket as well. If you have NUMA issues, that's part of the customizable grouping, and you can see whether the work is evenly divided or whether you may have some NUMA issues.
So if you click the package 0 for the demand, you will see the unit 0 and 1 instead of channels. Why is that?
I think that's just a naming convention. It may change. I think this is synonymous. It's the same as channel, just a naming convention.
And in this case, you can do about 20 gigabytes per second. In the previous one, it's just like 12 gigabytes per second. So this means like if you make only read from demand, you can actually. Because I kind of have difficulty understanding the quick performance, like why suddenly you can push to 20 plus gigabytes per second.
Yeah. So the reason at a high level is that the latency of a persistent memory write is much higher than a persistent memory read. So if you're doing a lot of writes, then your bandwidth goes down.
Okay.
And Suda has a lot of actual numbers and technology reasons for that. But at a very high level, just think to yourself, writes are worse than reads. I should do more reads, less writes.
Got it.
But obviously, sometimes you need to do writes. It's just a performance thing.
Right.
So now we can see, as we've done only reads, the available bandwidth goes way up because the writes are higher latency. But we're still not done. Let's see what else we can do. If we jump back over to our slides. We were able to eliminate the writes, but let's examine the code. So we see the functions in our result here. Parallel 4 is the hottest one, obviously, right? But there's a not insignificant amount of time associated with these pmemobj functions as well, right? These are some PMDK macros, and we're seeing time associated with those. Let's look deeper at what these are. If we double-click on them, will take us to the line of source code if we have it available. If not, I'll have to plug it in just like we did for the other examples. In this case, we do have it. And now I'll show you a feature that I actually haven't shown you yet. I think I have the binaries on here. I'm not positive. You may have them on yours. Let's see what happens. Click on assembly. In addition to seeing lines of source code, now we can see we're actually in PMDK here. These are PMDK lines of source code. We can see assembly, right? So if you are an engineer that likes to go to the lowest level, you want to see the assembly code and how it's performing, VTune can do that as well, right? And if you select a line of code in the C, it will highlight the lines of assembly that were generated by the compiler. Right? So if you want to see whether your code is vectorizing, how your compiler is behaving, what instructions are generated by any line of source code, VTune will show you that. And now, as we look, what we're learning here, as we see these functions, is that they're from this D read macro.
from obviously PMDK, where we have these read macros. So this is preventing the compiler from vectorizing. And if we look at the assembly, depending on whether you're an expert in assembly, let's see, I think I have to go up in the call stack. So let's just jump over these slides. If we look in the assembly here, if I have this line selected, and I look at the lines of assembly that are generated, you'll see here really basic x86 instructions. Move, imul, add, move. Anyone who's done assembly code knows that vectorized instructions look different than that. They might look like vmove, or I don't know off the top of my head, but AVX moves have Z moves, or different registers here for vectorized instructions. And vectorization is another huge part of performance on the latest platforms, right? We know the clocks aren't getting faster. What we're getting is more cores and wider vector registers. So if you can vectorize, you can get a lot more performance. In this case, the compiler did not generate vectorized code. So what can we do? Well, we need to read the data from the persistent memory. We can't just get rid of all the macros and say, well, now we've done better, right? That defeats the purpose of profiling Optane DC persistent memory. But we don't have to read the value from persistent memory over and over again. Once we've read it from persistent memory, we can then use the data that was read from persistent memory in the caches or in the DRAM, right? So move the macros outside of the loop and just read them once from persistent memory. In that case, you can see here, we just took the reads of A and B from inside the loop to outside the loop, and let's see what's changed in our performance. Now we've gone up to 26 gigabytes per second, right? We've made the bottleneck of persistent memory even smaller by adding vectorization. And if we look at the code in VTune with our next result, MA-vec default, I'll open that up here, and you can open it up if you're following along. I'll go to my bottom up tab. This should all start to feel familiar to you, right? I'm drilling down. First place to drill down to is the bottom up tag. Then I'll drill down. And you see here, actually, look at that. Those macros are gone, right? It used to be parallel 4 and then macro for the 3 hottest spots. Now it's parallel 4 and the macros are gone because I moved them outside the loop. They only happened once, so the time spent in those is negligible. It's almost 0. And now some other thing became the next hottest function, right? And let's see if we can drill down to source code. Let's see what we have in our slides so we make sure we're following along. Here we go. So this is what vectorized instructions look like. Now the heart of this kernel is being vectorized by the compiler. I have move with these XMM registers. These are your vector registers on your machine. The code looks more complicated than what you might have learned in your first assembly level class, but that's because it is more complicated. It's vectorized, it's doing single instruction, multiple data things, right? You can do maybe 4 moves or 8 moves or adds in the same instruction. And the compiler did this for me. I didn't have to hand code any vectorization. Once I moved those macros outside of the for loop, I got vectorization for free from the compiler. So as expected, the compiler was able to vectorize the code. Let me see if I can show you how you can see that in your application. So I double-clicked on my function. It came to this line of source code here in the GUI. Now I'm in the GUI, I'm not in slides anymore. Here's my multiply, and I'll click on assembly. And side by side, what I'll see if I select this line, source code, there it is, right? Yeah, it's all over. So this is all, actually, it's all over here. This is all right, so here it is. Yep. So you can do this. Click on this line of source code. There will be a little, it's kind of cut off, just to the right of this, it's in the black margins here. There's actually some shading of blue that shows you where in the file you want to be looking. But now I've got vectorized code here. Any questions? Okay. So, depending on how much of a vectorization expert you are, you may or may not know what you're looking at, but what you're actually looking at is SSE code. There's varying degrees of vectorization. A long time ago, we came out with SSE code, and that can do maybe four integers on a given instruction, right? Maybe it's 128 bits, I don't know off the top of my head. But beyond SSE, we've created new, wider vectorization instructions. 256 bits, or 512 bits in the case of AVX2 or AVX512. And depending on the processor you're on, you may have access to those. If you have a really old processor, then you may only have access to SSE. But if you're on a Skylake or something, then you should be using top-of-the-line vectorization instructions. So let's rebuild using this compiler flag and say, hey, I want you to build AVX2 instructions. I want you to build this for a machine that can support AVX2. Right? I don't know how many of you actually look into the make files of the applications you work on or look into the compiler flags that are used, but the compiler is the one that's usually in charge of creating vectorized instructions. So if you're not taking advantage of vectorization, it's another topic for another day. We have tons of tools to help you do that. So rebuild. Any questions? Okay, so we just put this flag to the compiler and rebuilt the code. When we did that, let's just see. We're not getting the same 2x that we used to, right? Now we're at 26 gigabytes per second. But once I vectorize with AVX2, I'm getting 27, right? So it's not 2x, but it's another 4% or something, right? Now I'm all the way up to 27 gigabytes per second. And we can still investigate the code by opening up the AVX 256 result that you all have access to. So let's open up the AVX 256 result just to verify that I'm not making this up. It's actually what was collected. And I'll do the same thing. I get a summary here. Also, just to note, you saw a bunch of little warnings there. You might see those when you run the tool yourself. All that's saying is I don't have symbol information for these modules that I profiled, right? They weren't built with debug symbols. Nothing to worry about if it's a module that you don't care about. All of your kernel modules and things may not have symbol information. The only ones you need or you want symbol information for are the ones that you want to see source code for. Right? If you want to see source code for the files that you're profiling, make sure you build them with debug symbols. You don't have to do a debug build, it's not optimized, but if you want source code level data, you do need symbols. So that's just an aside, because some people, when they use VTune for the first time, they get worried by all those warnings, but it's just telling you that there's no debug symbols for those modules. So now I'm in my summary view again. I can go to the bottom-up view. And then I can inspect the functions just like I did before. Using 27 gigabytes per system memory bandwidth. My macros are still gone because I've moved those outside the loop. I'll double-click on this function, the hottest function in my code. I'm just doing the same thing I was doing before. Repetition is good for understanding. That way you guys can remember what you saw here today. And I'll click on assembly. And you'll notice that the instructions look similar, but not the same. Each version of vectorization instructions, SSE, SSE2, AVX, AVX512, looks slightly different. I don't know how much you recall, but these used to be XMM registers for SSE. Now you're seeing YMM registers for AVX. So these instructions are AVX2 instructions instead of just basic SSE instructions. And that gave me even more performance because I'm able to do more instructions on any given cycle. Just same thing in the slides. We can confirm now via inspection that we're using AVX instructions. And if you can recall, I went from, I think, 12 gigabytes per second all the way up to 27 gigabytes per second in a step-by-step process, identifying what the performance issue was, changing the code, running the profile again, seeing what changed, seeing what the new performance issue is, and optimizing that. Right. So at this point, I've shown all the results that I want to share using this traditional VTune amplifier. Does anyone have any questions? Next, I'm going to show the platform profiler tool. Any questions on what we've seen?
Do you have examples for the log analysis?
We have examples, and actually the tool itself has a matrix multiply example included that has a little bit about parallelism, but I don't have one here today. I can give you an idea of what you'll see. You'll just see performance information about things like spin time and wait time. It will tell you, you can tell how big of a fan I am of this grouping by how often I keep going back to it. But you can also sort by, let's see if I have it here. Yes, I did not. So if you do a LOX analysis, one of the things that will be listed here is synchronization objects. So critical sections, barriers. It's not listed here because I didn't do a threading analysis. I don't think it's listed here. Yeah. But if you do a threading analysis, you'll see synchronization objects. And what it does is VTune will instrument every mutex acquire, every mutex release, every barrier, every critical section, and then it will break down the wait time for every one of those synchronization objects. So you'll see this synchronization object had 25 seconds of wait time. You'll double click on it. It will take you to the line of code where you see lock acquire or barrier or something, and you'll be able to figure out, oh, right here I have a lot of contention or a lot of wait time or something like that, right? So I don't have that example here, but that's what you'll see. You'll see wait time for each of your synchronization objects, and you'll see some additional information if you're using OpenMP or threading blocks. Do you know what threading you're using? Is it native threads?
Native threads.
Native threads. Okay, so native threads will also have that instrumentation built in. If you have any applications that do their own threading library, right? They don't use native threads. You built your own thing from scratch. All you have to do is use a simple API that we have included, and we can profile your threading as well. You just tell us, here's the lock acquire function that I've written, here's the lock release function, and we can collect data for your own, created threading library.
Thank you.
Sure. Any other questions? Yes.
You can choose how can we collect the result data?
How can you collect the result data? Sure. So what you would be doing here to collect this data, is you would start from the welcome page, right? And you would create a new project. This is all in the GUI. You'd give it a project name. And then you would say, what do you want to collect, right? So localhost means I want to collect on this machine. You can also do a remote target with SSH. You can configure an arbitrary target where I want to do the configuration here, but I will copy it over to the other machine later. But that's where you select where you want to do the profile. Then you say, what do I want to profile? Maybe I want to profile, I don't have something here, but c:/InternetExplorer.exe or something, right? Or /home/user/my-application, whatever. Whatever you want to profile.
The executable file.
The executable file, yes. And if there's any command line parameters, you type them in right here. If you need to pass some command line parameters. And then there's some advanced things that you can investigate as well. If you want to attach to a running process, you would change it here. You would say instead of launching the application, I want to attach to a running process. Here's the process name, or here's the PID, right? That's running, and then you can attach to a running process. Or you can say I want to profile the entire system. I want to profile all of the processes. So that's what you do. You choose what you want to profile. Then over here, you choose what type of analysis do you want to do. Do you want to do hotspots? Do you want to do memory access? Do you want to do threading analysis? Right? You choose the type of analysis, and then you click Start right here, and then that will start the profile. Yeah, go ahead.
Is there any sound to do compile time?
At compile time, the only thing you need to do is generate debug symbols. So like -G on Linux or /G on Windows. And the reason you need to do that is if you want source code information for the performance data. But nothing else at compile time. You can use GCC, you can use ICC, whatever you want. And then one other thing I'll mention is, so you can even configure this here and say, here's the PID, here's everything. But if you want to run on another machine, you just click this command line button, and it pops up the command, right? And then you just copy this command to a shell somewhere else, and you can run it without needing the GUI, right? And this is the really useful thing. You don't have to memorize all of the flags for VTune, all the command line flags. You just configure them in the GUI. You click this button, and it gives you the command line to do that type of thing. So that's how you set up the analysis in VTune. You choose where you want to profile, what you want to profile, and how you want to profile. And then either just click play to start the profile, or get the command line if you want to copy it somewhere else. There's also a ton of other powerful collection control features. This one here is start paused, so you can start the application but not have collection running, and then start the collection at a later time. Maybe you need to get some input from the user, or there's a bunch of startup initialization that you're not interested in profiling. You can start your application with the collection paused and start the collection later. There's also an API to start and stop collection or pause collection. So you can put an API inside your code that says start collection here, stop collection here, and it will only generate profile information for that region. You don't have to profile everything. If you want, you can control the collection manually.
Could the user for Linux kernel for function level, and what about the instruction?
Could you, sorry, one more time?
Could the VTune user for Linux kernel?
Yes.
What about the function level? What about instruction? For example, a syscall. A syscall is not for read or write, or read or write disk or network is how to choose.
Yes.
Use VTune.
So if I understand the question correctly, can you profile kernel level?
Yes.
Yes, you can. So as long as you're using the hardware collector, the one that uses the PNU registers, you can profile the kernel and kernel drivers as well. If you have source for the kernel, you can actually see all of the time spent in the kernel using VTune. So you can profile at the low level, instruction or function level inside the kernel. Does that answer your question? You can ask again if you want to ask in Chinese, if that's easier. Got it? Okay. Yeah. So you can profile the kernel and you, at the function level, the instruction level, inside the kernel, no problem.
关于这个 Linux 可能的时候，可能本身那个给你系统，给你所带的，或者是你自己做那个 CPU 的时候，为了那个自己的这个可能会
因为我看到它的例子都是关于那个这个 CPU 计算类型相关的，是没有那个函数之类的。因为很多时候我们学术是一个很大的系统，整个路径很长，然后就是一般可能就是这个读写啊很慢，然后就是它跟系统调用比较慢，对吧？
这种的话就不太好用VTune，因为你的函数只有它在花 CPU 的时候才能够被VTune这个3D 给抓到。所以如果你的函数调过去以后，然后 I/O 那个就是内存代码执行完了去访问一个 I/O， 然后这个时候系统 CPU 就进到16状态了，CPU 本身不工作了，对吧？这个时候你的 CPU 里面就是有一个，那这段时间的话，VTune这个是非常抓不到你的这个，但是有其他的方法，比如说你可以在你的那个代码里面加一些这个什么时候开始的，什么时候结束的。这个 API 来告诉VTune，然后它就能够把这个时间区间给你在VTune里面，就是在结果里面就标注的，这样的话基本上看出来这段时间多长时间是多长时间，这个 是可以在结构里面展现出来的，那是属于比较高级一些的。可以去搜索一下那个微信的那个 IPG 文件，用这些图板，就是去推新的动作。
So the last feature I want to talk about is called Platform Profiler. I'm not sure if any of you saw presentations on it, but Platform Profiler is a little different than what I've been showing so far. What I've been showing so far is the traditional VTune that was designed at profiling applications and figuring out the performance for software developers to tune it. Right? Platform Profiler is a new feature that's designed at profiling an entire system and understanding how the resources on that system are being used, but not necessarily tuning a specific application. Right? So it's included in VTune Amplifier, but it's set up a little bit differently. In VTune Amplifier, you set up. So let me actually mention really quickly the way that Platform Profiler works. Is there's a very lightweight collector, and you can run this collector on any machine, and it can run for a long time. It can run for tens of hours. This is a different kind of sampling that doesn't create large amounts of data, so you can profile long-running workflows. And you have this lightweight collector that generates some data. You also have a server that is used to analyze that data. And you take the data that's collected, you upload it to the server, and then you do the analysis on the server. Right? The server can be the same machine if you want it to be, or it can be some other machine in your data center, or some machine somewhere else. Right? It's just a slightly different model. You're not using the traditional VTune GUI, you're using a web-based server. So the server is actually launched through VTune. Right here you see Platform Profiler, and if you launch the GUI on some machine, you'll set up the server using that. So I've already done it on my laptop, but for you, you would click on Platform Profiler. First, there would be a button here that says Configure Platform Profiler. You'd do that first, and then once you've done that, you would launch Platform Profiler. After you've launched Platform Profiler, there will be a lightweight web server running on this machine. And I can actually navigate there by going, in this case, opening up a Chrome browser, go to localhost /6543, and you'll see this right here. So this is the Platform Profiler server, and I have some options here. I can look at some samples, get some documentation, look at results that I've already started, collect data, or get some help. In this case, I didn't give you guys workloads for Platform Profiler because there's some already included in the server. So let's just quickly look at a couple of those samples. So if you go to View Samples, you'll see there is some data collected for a matrix multiply, some data collected for a file copy, and some data collected for a memory access workload. The way that the data is collected, so this is all the server where we're analyzing the data. The data is actually collected via a lightweight command line application. So you install the collector on a machine, and then you use commands like VPP collect start and VPP collect stop. These are the types of commands that you run on the machine where the workload is running. It will create a result, and then you'll upload the result to Platform Profiler. So if I was going to look at some results here, here I can go View Results. Here's where I would upload new results. I can go to a directory that I've created, or I can go to the samples directory. Inside the samples directory, I'll see these results. And maybe I'll open up the matrix multiply samples. Now, if you've attended the Platform Profiler section, you've seen things like this before, but I'll just quickly mention a few things. We have a topology diagram that shows you how the sockets are laid out, how the memory DIMMs are laid out, and where you have devices connected. We're seeing metrics like memory utilization. Is your application consuming a lot of memory? If memory is a bottleneck for you, you may see high memory utilization. If you're doing something like Optane DC persistent memory, this is a very important metric. In the matrix multiply sample, we actually have just a performance issue kind of related to CPU utilization. Right? So this application was running on a machine that has lots and lots of cores available to it, but the parallelism was not done very efficiently, and you can see that CPU utilization is very low. We'd like to see this number much higher. And you can see here that let's look at another sample as well. So here I've got let's get a dgen. Let me open up another one. Let's open up a file copy workload, right? So this workload was doing more disk accesses. You can see here, this one ran for, let's see, this one ran for about 600 seconds, and you can do much longer runs. If I hover over the I here, it will give me information about the system that it was running on, what type of processor was it, when was it run, how much memory was available, that sort of thing. If I look at the view, it can be changed. You can do an overview, you can do core, memory, disk. In this case, it was a file copy. So let's go ahead and look at the disk metric view, see if there's anything interesting there. You see disk read and write throughput, read and write latency. One thing that's important to note, you're not seeing process names here, right? You're not seeing function names. You're not seeing source code. That's not what this tool is. This is a platform profiler. It's giving you information about the resources on your platform over time and how are they being utilized, right? Again, you can zoom and filter just like you can with the other types of analysis. If there was something interesting, if you zoom in on it, on any timeline, doesn't matter what the metric was, it'll update all the timelines. You can actually see right here, here's the chunk that I zoomed in on. Now my metrics are just reflecting that small piece of time. And so in addition to disk, you have CPU utilization, you have memory utilization. There's metrics for Optane DC persistent memory. They're not in the samples, but we have Optane DC persistent memory bandwidth. You can see memory bandwidth broken down by channel. So if you want to see whether you have configuration issues, this is a disk workload, so there's not a lot of page faults or anything like that. But those metrics are there as well. And as you explore this tool, you'll see that there's a lot of metrics available, and this one is still under development, so we're really looking for feedback. If people have input on what metrics they'd like to see, if we don't have those available, or something like that, we're very interested in getting feedback on this, so let us know if this tool is useful for you and there's something you'd like to see to improve it. We're open to hearing that feedback. I think we've just got about 5 or 10 minutes left. Since this is a hand-on session, I'll stop a little bit early. If anyone has questions, feel free. I'll hang out here. I'll walk around and help folks if they were able to install VTune and look at some results. There's other people here that know VTune as well. But other than that, thank you for attending the session, and I hope you are all able to try out VTune and let us know what you think.